In this lesson, we're going to transition to a very different topic than the topics that we've already seen in this course. And this is a topic that's extremely important throughout mathematics, not only in algebra, but in trigonometry, pre-calculus, and even beyond. It's the idea that we call a function. So let's start, as lots of mathematicians like to do, with a definition. So here it is. A function is a set of pairs of input values and output values in which each input value is assigned exactly one output value. The set of input values is called the domain of the function, and the set of output values, or things that come out of the function, are called the range of the function. So we have a function, which is defined to be a set of pairs, inputs and outputs. We have the domain, which is the set of inputs, and we have the range, which is the set of outputs. We'll often use notation like f parenthesis x parenthesis, which I'm going to pronounce f of x, to specify a certain function. So, for example, if we write f of x equals 2x plus 3, we mean that for any input value x that we plug into the function f, the output value will come from the rule 2x plus 3. So if I plug 0 into this function for the x value, then the output value is going to be written as f of 0, which is 2 times 0 plus 3, because the rule was 2x plus 3. And if I take 2 times 0 plus 3, that's the same as just 0 plus 3, which is 3. So f of 0 would be 3. I could also plug in 4 for x, for example, and the 4 would be part of the domain of the function, and the output value would be f of 4, which is now 2 times 4 plus 3, which is, according to our order of operations, 8 plus 3, which is 11. So the 4 would be in the set that we called the domain, that's the input values, and the 11 would be a member of the set we called the range, the set of output values. Now, it would probably be helpful to talk about lots of examples of things that are functions and even things that are not functions, as well as domains and ranges. These are very new terms for many of you, I'm sure. And so I'd like to walk through several examples to talk about what a function is, what's not a function, and if I am looking at a function, what its domain and what its range is. So here's an example to try to keep us going in this line. Consider the equation f of x equals x squared, x to the second power. So here's my question. Is this a function? Well, I'm going to tell you right now that it is. Yes, it is. And the reason it is because, according to the definition of a function, for every input value that I plug in, x, I need to have a unique output value, in this case, x squared. So I'm going to have that definition satisfied by the rule f of x equals x squared. It really will work. And now let's just try plugging in several values for x. Those input values are from the domain. And let's see what the output values, or the range elements, look like. So for example, f of 0 is 0 raised to the second power, or 0 squared, and of course that's 0. So when I plug in 0, I get 0 back. That's perfectly legal to have the same input and output value. No problem there. When I plug in 1 to f, I would have f of 1. That's 1 squared, and 1 squared is 1 times 1, which is 1. Again, notice I had 1 as the input value and 1 as the output value. No problem. What's f of 2? Well, f of 2 is 2 squared, which is 2 times 2, which is 4. So the domain element 2, or input value 2, is connected to the output value 4, and that 4 is part of the range. And lastly, f of 3. When I plug 3 in, I have 3 squared, and 3 squared is 3 times 3, which is 9. So the input value 3 is connected to, if you will, the output value 9. There's no ambiguity as to what each output value is going to be. There's no confusion as to, well, if you plug that in, I'm not sure what's going to come back. Functions always know when you plug in a certain input value, what the output value is going to be. There can't be any confusion or questioning whatsoever. Notice that I could have also plugged in some negative values. That would have been perfectly fine, so let's do that. What if I wanted f of negative 1? Well, that would be negative 1 squared. Now let's be careful. That's the same as negative 1 times negative 1, and the two negatives cancel each other, and you just get 1. So the input value, negative 1, has an output value of 1. F of negative 2 is negative 2 squared, which is negative 2 times negative 2, and again the negatives cancel with one another, and I just get positive 4 as the output value. Again, part of the range. That 4 is part of the range. And f of negative 3 would be negative 3 squared, which is negative 3, times negative 3, which is 9. All of this is perfectly fine. But I could hear a few of you saying something like, hey, wait a minute, time out. Notice that f of 2 and f of negative 2 were the same. They were the same output value. They were both positive 4. Is that okay? Do I still have a function if two different input values, 2 and negative 2, have the same output value of 4? The answer is yes. It's okay for a function to have two different input values connected to the same output value. What's not okay is to have the same input value going to two separate output values. That's bad when you're looking at functions. A function cannot have one input going to two separate output values. But that's not what f of x equals x squared is doing. It does have two inputs going to the same output. That's okay. That's perfectly fine. F of x equals x squared really is a function. Now, let's talk a bit about domain and range in this case. We saw a few numbers that go into each of those sets, but I'd really like to think about what the full domain and the full range looks like. So notice that you're actually allowed to plug in any real number that you want into f of x equals x squared. There's nothing about x squared that keeps us from plugging in any real number. We could have plugged in 19 or negative 103. We could have even gone crazy and plugged in pi or square root of 7. And that means that the domain of this function, the set of all input values that we can plug in, is actually the whole set of real numbers. And if you want to think of it as a real number line, that's fine as well. We would denote that domain with an open parenthesis, minus infinity to infinity, and then end that with a parenthesis as well. That means that we're going to include all of the real numbers in the domain. They're all legal input values, if you want to think of it that way. Now, what about the range? Okay, the range is the set of output values that are going to come out of the function. Well, the range in this case is a little different. Notice that you're never going to have a negative number as an output value of this function, because the output values are all squares, right? Even when you plug in a negative number into the function, did you notice you get positive numbers back? When we plugged in negative 2 as an input, we got positive 4 back as an output. So what's the smallest output that you can get from this function? Well, the answer is actually 0. And that happens when you plug in 0 for x. F of 0 is 0 squared, which equals 0. All of the other outputs are going to be greater than 0. Just like when you did f of 1, we got 1. F of 2 was 4. F of 3 was 9. So the range in this example is not the set of all real numbers. The range is just the set of non-negative real numbers, or the interval from 0 to positive infinity, including the 0. That means I'm going to denote the range here as the following. I'm going to put a square bracket, 0, comma, infinity, and then close with a parenthesis. The square bracket next to the 0 tells me that 0 is included in the set. So it's included in the range. Infinity is not a real number, so I'm not going to put a square bracket next to the infinity. I'm just going to put a parenthesis. So the domain in this problem was minus infinity to infinity. That's the set of all real numbers. But the range is just square bracket 0 to infinity. It's just basically half of the set of real numbers if you want to think of it that way. It's all of them from 0 on to plus infinity. All right, let's look at another example now of a function and even talk about its domain and its range. I want us to think about this function. F of x equals 4x plus 2. Now, I'm hopeful that for some of you, you're thinking, hey, that looks a lot like y equals 4x plus 2. And we already know what that is. That's the equation of a straight line. Well, the same is true for f of x equals 4x plus 2. It's just a function whose graph is a straight line. So what we've learned about lines already in this course helps us to understand this example. Now, let's talk about its domain and its range. Well, there aren't any numbers that we can't plug in for x. Everything you want to plug in for x that comes out of the set of real numbers is perfectly fine. So the domain is the set minus infinity to infinity. It's the set of all real numbers. What about the range? Well, turns out that the range, which again is the set of output values that's going to come from the function, is going to cover every possible y value you can imagine if you want to think about it on the y-axis. So the graph, remember, it's just a straight line. The graph is actually going to go from minus infinity in the y direction all the way up to plus infinity in the y direction as well. And that means that the graph tells me what the range of this function is going to be. It's going to be the interval, again, from minus infinity to infinity. So here's an example where the domain and the range are actually the same set of numbers. Now, let's look at another example. Take this function, f of x equals square root of the quantity x minus 3. Now, believe me, it's a function, but I'd really like to think about this one in terms of domain and range. So let's talk about those as we work through. Let's start with the domain. Remember that the domain is the set of input values that we're allowed to plug in. Now, let me ask you a question. Can you and I ever compute square root of negative 5? Well, the answer is no. What about the square root of negative 9? The answer is again no. Notice that square root of negative 9 is not the same as negative 3. Some students fall into that trap. It's very tempting to say that the square root of negative 9, is negative 3. But the square root of negative 9 cannot be negative 3 because negative 3 times negative 3 is positive 9, not negative 9. So the square root of negative 9 as a real number doesn't make any sense at all. In fact, square root of x minus 3 as a function can only be computed if the x minus 3 part is greater than or equal to 0. And that's the same as saying that the x has to be greater than or equal to 3. Well, guess what? You and I just figured out the domain of this function. It's got to be all the numbers starting at 3 and going to plus infinity. And the way we denote that is square bracket 3, comma, infinity, and again, a parenthesis next to the infinity because infinity is not a real number. Now, what about the range of the function? The range is trying to tell me what happens with the y values or the output values of the function. Well, you and I both know that the square root of anything is always going to be either 0 or positive. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and so on. What does that mean about the range? It means that the range is the set of all numbers from 0 to plus infinity. And I can write that as an interval, bracket 0, comma, infinity. Now, let's look at one last example about these domains and ranges really quickly. Let's think about f of x equals x divided by the quantity x minus 2. So I have x on top divided by x minus 2. Now we're going to talk about these kinds of functions later in the course where we have a piece on top divided by a piece on the bottom, x divided by x minus 2. But I want to think about this example today just in terms of domains and ranges. So here's my question. What values would give us a problem to plug into a function like x over x minus 2? Well, there's no problem with the x in the numerator. I'm allowed to plug in anything I want there. But the denominator might actually cause me a bit of trouble because of division by 0. You and I both know that we can't ever divide by 0. Notice that if we try to plug in x equals 2, we will have a problem because f of 2 equals 2 divided by 2 minus 2, which is 2 over 0. That's not defined. We can't have a 0 in the denominator. And therefore, x equals 2 cannot be in the domain of my function. I cannot plug 2 in. Notice, though, I can plug anything else in that I want as long as I avoid 2. So it turns out the domain here is the set of all real numbers x not equal to 2. I just have to pluck the 2 out and throw it away. I can keep all the other real numbers. That will be my domain. All right, we've talked enough about domains and ranges for now. I'd like to say a few words about some more terms that we have with functions, and then I want us to talk about how to combine functions using addition, subtraction, and so on to get new functions. Okay? So throughout the course, we're going to talk about some different notations for functions. Things like f of x equals x plus 1. I could also call it g of x equals x plus 1. I could have called it y equals x plus 1. I might even have things like h of t equals t plus 1, and things like that. The names of the functions and even the variables aren't the important thing here. What's important is that we know what the input value is and what the output values are. So in an equation like y equals x plus 1, we normally think of the x as the input and the y as the output. Or to use some fancier language, we think of the x as the independent variable and the y as the dependent variable. That input variable doesn't depend on anything else, but the output variable always depends on what you plug in. So that's why we're calling the input the independent variable, and the output we're calling the dependent variable. We won't use this language too much, but we will use it every once in a while, and you'll find it in lots of other textbooks too. So I wanted to make sure we hit on it before we moved on. Now, let's talk about how you can combine functions using different operations just to make sure we know how to build bigger and bigger functions out of smaller and smaller functions. So you already know about things like addition and subtraction and multiplication and division from just doing arithmetic. Well, it turns out you can do the same sorts of things with functions. So let's look at a couple quick examples. First of all, let f of x equals 5x plus 4, and let g of x equal 2x minus 10. Can you find f plus g and f minus g? If you want to try, stop the video at this time. Okay, let's try to do these together now. F plus g and f minus g. First of all, just so you know, f plus g is a new function. And f minus g is also a new function, which uses the f and the g and puts them together. So we're going to build new functions out of old ones. First, f plus g. It's exactly what you think it is. You just take the 5x plus 4 plus 2x minus 10. And when you add those together, you're going to have 5x plus 2x plus 4 minus 10, which is 7x minus 6. It's a new function, 7x minus 6. What about f minus g? Well, now you got to be a little more careful. It's going to be 5x plus 4 minus the quantity 2x minus 10. And now that minus sign that's sort of in the middle needs to be distributed into that second set of parentheses. And you'll have 5x plus 4 minus 2x plus 10, because minus times minus gives you a plus, and that's the same as 5x minus 2x plus 4 plus 10, which is 3x plus 14. Don't lose that minus sign. It's got to be distributed as you go through. Now, let's try something a bit harder. I'd like to try to find the product of two functions very, very quickly. Remember, product just means multiplication. So let's try that here. Let f of x equal 5x and let g of x equal x plus 4. Let's find f times g, which is the product of f and g. Well, F times g is exactly what you think it is. You just have to multiply the two terms together. And f times g is going to be 5x times the quantity x plus 4. So I have to distribute that 5x in, and I'm going to have 5x times x plus 5x times 4, which is 5x squared plus 20x. Now notice, we started with two linear functions. 5x and x plus 4 are both going to give you lines if you draw their graphs. But we now created something that's not linear because it's got an x squared in it. Really cool. So you can actually start with two linear functions, multiply them together to get something totally different. Now, what would f divided by g look like? Well, f divided by g would just be 5x on top divided by x plus 4. And unfortunately, there's nothing else you can do with that to make it any cleaner or more simple. So we just leave it that way. It's still a very interesting function though, because now it even has problems with its domain. Notice you've got to avoid division by 0 at that point. So even f divided by g is a new function, and it's got some interesting properties as well. Now, in this lesson, I'd also like to talk about an operation which you may or may not have seen before, and it's a very important operation in building new functions, especially as you go on to higher and higher mathematics. It's called composition. In a nutshell, if you want to compose two functions, it's like plugging one of the functions into the other function. So it's not multiplying them together, it's actually taking one of the functions and plugging it into the other. So let me show you an example. Let f of x equal 2x plus 4 and g of x equal 3x plus 2. I want to find the composition of f and g. Now, to do this, let's talk about a bit of notation first. The composition of f and g is going to be denoted as f of g of x. Now, notice how it looks like we actually plugged g right into f. It's like we forced it in. That notation is trying to tell us what we really want to do. We want to take the rule for g, which is the quantity 3x plus 2, and we want to plug that in for f. We want to plug that in for x in the rule for f of x. So I'm going to take the 3x plus 2, and I'm going to plug it in for x everywhere I see x in the rule for f. And this is what we would have. F of g of x would equal 2 times 3x plus 2 plus 4. Do you see how I took the 3x plus 2 and actually put it into the role of the x inside f of x? And once I've done that, I can actually simplify. So f of g of x would be 2 times 3x plus 2 plus 4. I distribute that 2 to give me 6x plus 4 plus another 4, and that gives me 6x plus 8. So f of g of x in this case is 6x plus 8. Now, there's something cooler you can do here. You can also find g of f of x as well. Now, let me suggest you try that yourself. Remember, you're just plugging in all of the function f into the x part of the function g. You're actually plugging them right in. So, let's try that. All right, let's do it together now. If we want g of f of x, it's going to be 3 times 2x plus 4 plus 2. So I've taken the 2x plus 4 and plugged it in for x inside the rule for the function g. So I have 3 times 2x plus 4 plus 2, which is 6x plus 12 plus 2, which is 6x plus 14. Now, let's do a bit of critical thinking together. I want you to look at something. Look at f of g of x and look at g of f of x. They're both functions. They look kind of similar, but notice that they're different. They're actually two different functions. Most of the time, almost all of the time in fact, f of g of x is not going to equal g of f of x. Sometimes they're equal. And that's going to tell us something very special about f and g. They have a special relationship when f of g of x equals g of f of x. But I'm going to save that topic for another day. We'll see that idea of f of g equaling g of f later on. Maybe even if you take a pre-calculus class, you might see that more and more. But most of the time, f of g will not equal g of f. All right, let's look at one more composition problem just to make sure we've got it down. See if you can do the following composition. Let f of x equal x squared and g of x equal x minus 7. I want you to find f of g of x and g of f of x. Okay, what answers did you come up with? Well, let's start with f of g of x. I'm now going to take g of x and plug it in to f, and when I do that, I'm going to have x minus 7 squared. And there's nothing really more to do. If you'd like to expand it, you're welcome to do it, but actually, you can just stay with x minus 7, the whole thing squared. All right, now let's do g of f of x. So now I'm going to take the rule for f of x and plug it into g. So I'm going to replace all the x's in the g function with whatever the rule for f of x is. In that case, it's x squared. So g of f of x is x squared minus 7. There's nothing else to do. It's just x squared minus 7. Now, here's a question. In this example, is f of g of x equal to g of f of x for every value of x? So let's plug in x equals 8 into both functions and see what we get. F of g of 8 equals 8 minus 7 squared, which is 1 squared, which is 1. While g of f of 8 equals 8 squared minus 7, which is 64 minus 7, which is 57. Notice that these two output values are different. So f of g of x is not equal to g of f of x in this case. All right, we've spent some time talking about new terminology related to functions. We've discussed some of the operations that can be used to build new functions out of old functions. I'd like to close this lesson with a visual idea again for how we can tell whether a specific graph is the graph of a function. I'm not going to worry so much now about the rule for the function or its domain or range. I just want to know, if you hand me a graph, can I tell quickly whether it's the graph of a function? And this test is going to be called the vertical line test. Here's how it works. If you can draw a vertical line that crosses through at least 2 points on a graph, then we know that that graph does not represent a function. So let me repeat it. If you can draw a vertical line that crosses through at least 2 points on a graph, then that graph cannot be the graph of a function. So let me show you some examples. Let's start with the graph of a circle that's centered at the origin and has radius 2. It would look something like this. Now, all you need to do is be able to draw one vertical line through this graph. If that vertical line crosses more than 1 point, then this graph cannot be the graph of a function. Well, in the case of a circle, you've got all kinds of choices for where to put that vertical line. In fact, just take the y-axis as it's drawn right now, and you can see that the y-axis crosses a point at the top of the circle and a point at the bottom of the circle. As soon as that happens, it means that the circle is not the graph of a function. Okay, let's try another example. Let's take this graph, which looks a little bit like a sideways U, so to speak. And I want you to think about it for a second. Is this the graph of a function? Well, just like with the circle, I can draw a vertical line that crosses through this graph at 2 points. It's pretty straightforward, in fact, to see that the y-axis again crosses 2 points on the graph. But it doesn't always have to be the y-axis. As long as you can find one vertical line that crosses the graph at 2 or more points, then that graph cannot represent a function. So this sort of sideways U graph definitely does not represent a function. Okay, let's try instead something like y equals x squared. We saw in the previous lesson that the graph of y equals x squared looks like this nice U shape going through the origin and then going up. Here's my question. Function or not a function? According to the vertical line test, this is a function. Notice no matter where you put that vertical line, it's going to cross the graph in only one place. So by the vertical line test, this is the graph of a function. Well, in this lesson, we've talked a lot about functions. We've laid a lot of groundwork for lots of future conversations that we'll have about functions as well. We've talked about domains and ranges, and we've talked about this vertical line test, which is a visual way of seeing whether a graph is a function or not. Next time, we'll return to thinking about linear equations again, but this time we'll talk about systems of linear equations, two equations that are there together, and finding solutions for those systems. I look forward to talking with you then.